So let's do an example. And the example goes like this. Yes. So first I'm going to define us a nice sequence. So define the sequence AN as follows. So we're going to have, actually, let's call it HN just to be different. So you have H0 equals 1. H1 equals 2. And H2 equals 3. These are our initial conditions. And then we're going to recursively define this sequence. So we're going to have H of K equal to the 3 previous terms for all K greater than or equal to 3. So what that means is that we're trying to calculate H of 3. Well, that's just going to be the sum of the 3 previous terms. That's going to be H of 2 plus H of 1 plus H of 0, which is 3 plus 2 plus 1. And then H of 4 is going to be H of 3 plus H of 2 plus H of 1, the 3 previous terms, which is H of 3 found out 6, H of 2 is 3, H of 1 is 2, so it's going to be 3 plus 6 plus 2, which is going to be 11. On and on like that. So here's the claim about this sequence. The claim is that for all n greater than or equal to 0, so for all integer n greater than or equal to 0, the nth term in the sequence is less than 3 to the n. Less than or equal to 3 to the n. That's the claim. And we can see it kind of makes sense, right? Like H of 0 equals 1, which is less than or equal to 3 to the 0, which equals 1. H of 1 equals 2, which is less than or equal 3 to the 1, which equals 3. H of 2 equals 3, which is less than or equal to 3 squared, which equals 9. I'm sorry, yeah. H of 3 equals 6, right, which is less than or equal to 3 cubed, which equals 27. H of 4 is 11, less than or equal to 3 to the 4th, which equals 81. So this seems to make sense. For all the values we're checking, we're getting that H to the n truly is less than 3 to the n. So this right here, we'll call this our P of n. P of n is true if H of n is less than or equal to 3 to the n. So I think the best way to actually prove this is true is with strong induction. The reason being, we can't really use a direct proof on this. I wish we could, but the issue is we don't really know what Hn is. For any n, we kind of have no idea what Hn is. We only know what it is relative to its previous values. So it's hard to say, like, let n be any arbitrary element of natural numbers, consider H of n or something like that, because, well, H of n is meaningless at the previous values. But this is exactly why induction makes so much sense, because induction is the way to prove the next value from the previous values. So it makes total sense. Total sense that induction might be the key here. So I'm going to say proof by strong induction. Proof by strong induction on N. Now we're going to come back to the base case. The reason being that we kind of have to see how our inductive step works first. We kind of need to know what does our inductive step need before we need to know how many initial conditions we need. You'll see that in a second. So if we look at our inductive step, we want to show that for all n greater than or equal to some b, whatever it is. Well, we know in the base case, we know we're going to start at 0. So we're going to have to at least have that. So we could say let n equal 0. Note that h of n equals h of 0, which equals 1. By definition, 1 is less than or equal to 3 to the 0. We know we're going to need to start with that base case at least. We might have more in between. Let's see what the inductive step means. So the inductive step is going to say for all greater than or equal to some b, we're going to fill that in a second. P of 0 all the way up to P of B, or sorry, P of N, can be used to prove P of N plus 1. That's the idea, right? So this is what we want to show. I.e., what we want to show is that for all n greater than or equal to b, if P of k is true for all k between 1 or between 0 and n,